Hello, welcome back. Hopefully things are going to start smoothing out a little bit with these presentations online. I have to tell you, I feel like a broken record because I keep recording these things a million times as I catch myself making mistakes or droning on too long about one thing or another. So I think my fiance and my dog are going to be very good at developing linear models by the time this whole thing is over, because they get to hear each of these lectures about 6 times before I get one that's acceptable to post. So, enough rambling. I will get into this here. We're on lesson 1.2, and you can follow along in the textbook, chapter 1.3. So when we talk about developing a linear model, if we're talking about a static system, meaning something that is only influenced by the current input, there's no kind of time dependency associated with it, it would be represented by the following equation. So clearly this y equals mx plus b is something that we've been dealing with since probably high school or earlier than that. And it's something that we're fairly comfortable handling. And if we plot something out and the data plots out to look like a straight line, we're fairly comfortable with handling. Where we start dealing with static systems, dynamic systems, it starts becoming a lot more complex. And you can see if all of a sudden y and x are changing as functions of time, in order to solve those equations, we're going to be solving different systems of differential equations. Now, we can set these up and we can have, very complex systems, but in order to actually come up with an analytical solution to them, you pretty much, or you don't have to, but it really makes life a lot easier if you can linearize your equations. So we're starting out here kind of with this y equals mx plus b kind of linear system. And we'll quickly transition into having differential equations, but we want to get them into this linear form if at all possible, so that we can apply kind of well-known analytical solutions to solving them. So that's kind of where we're headed to. All right, so the example that's shown up here right now is straight from the textbook, and basically there's a cantilever beam that's being deflected by some force that's applied to it. So we have a force, and the weight F is being applied to the beam, and it causes some amount of deflection. So my question for you is, if we put this into a block diagram form, and we have an input and we have an output, we'll say that our system is this cantilever beam. What is the input to the system, and what's the output of the system? Now, if you haven't kind of readily just sort of shouted out the answer to your computer, let's remember that the input to the system is the cause. So if we're looking at a cause and effect, the input is the cause, the output is the effect. So in this case, the weight is causing the beam to deflect. So the effect of the weight is deflection. So our input is the weight and our output is a deflection. So when we go back to talking about a linear model, if we want to know whether a linear relationship exists, if a linear relationship exists between f and x, then what would the relationship be? The output is the deflection, so we'll say that's x is equal to the some slope of a line times the weight, and we called that f, plus b if there was any intercept. So this is the type of form we're expecting. Now, if you look in the book on page 9, they give you data. I did not copy that data out for you here. I figured you could just kind of look at your... So when they plotted the data out, they chose to make this beam, the intersect here, at the 0 point. And it's kind of a logical choice, since if you have no weight applied to the beam, theoretically there's no deflection of the beam. That may or may not be true, but these are sort of engineering decisions that you need to make as you're deciding to plot the data. In this graphical type of an approach, once we plotted these data points out here and we see them plotted out, the person who was making the book basically put a ruler down here and created this straight line. The next person that came along could have made chose to lay down the straight edge slightly different, and may have ended up with something like what I just drew here in pink. So this is highly subjective, this type of a graphical approach. Once you plot out the data, then you can certainly see we came up on the other side of, or on the previous slide, and said that we would have an equation looking like something like x equals m times f, and where x is our output and f is our input. And we can figure out, or we can calculate the slope of the line based on the data points that are here. And that calculation is shown in the text of in the textbook on page, what is that on? On page 10. So we can go through and come up with something like this. And it all kind of seems fairly simple. When we get to chapter 4, we'll come across, and you may have come across this in your physics books, is that a beam has what's called beam stiffness. And that's a property that's generally represented by the letter K. So we'll say K is the beam stiffness. And the relationship between the force and the deflection and this beam stiffness is represented by force is equal to K times X. So from this beam stiffness is a physical property of each particular beam, made of a different material at a different temperature, and so on. And that property is going to be can be determined from the inverse, so 1 over m. And if we look at this, equation 1 here and equation 2, if we look at the two of these, it's clear where that relationship between K and M comes from. So once we come up with this model, in the case of this example, we had data and we came up with this equation 1. Later on in the book, once we know a little bit more about how, material properties and so on, we could have come up with this type of a relationship from the beam stiffness, in which case we would have started out with an equation and we could have plotted that to see the relationship. But regardless of which way we come up with it, once we have a model, you can interpolate to predict values for various inputs. So for example, if I wanted to predict what kind of a deflection I would get if I applied a force of 300 pounds, I can, look on the graph here. I could plug that into my model and get a prediction of, like maybe approximately 0.298 or wherever here. So we call that interpolation. And really interpolation is when we're predicting the output based on our model within the range of the data that we have. So the key part for that is within the range of the data. Extrapolation, on the other hand, and I've got some funny spelling here, is when we predict data, or when we predict the outcome when we're beyond the range of the data that we had. So for this example, if I was to try to predict what would happen at 1,000 pounds here, we could predict based on this original one that the output would be, maybe 0.9 or 1.0 inches. However, as soon as we start predicting beyond that set of data, it becomes kind of a dangerous thing because we really don't know what's going to happen. And if we think about this beam, really, the beam could break at 101 pounds. And it may just completely, snap off and we've got nothing coming out. All right, so I just wrote what I've been saying all along. So we'll move on.